Okay, in chemistry today, we're going to be talking about noble gas configurations. Right? So in class, we've been doing the electron configurations. For example, 1s2, 2s2, 2p6, and on it goes. And after a while, the hand starts to hurt because some of these can get really long and tedious. So there is a short, abbreviated way in which you can write these configurations. So a noble gas configuration. It's a condensed electron configuration, shows only electrons, the outermost subshells. Noble gas, what remains after the noble gas. So what this is you're basically taking the configuration of the noble gas and condensing it by simply representing that configuration by the noble gas electron configuration, by using the elemental symbol of that noble gas, which really shortens these. And then what remains after the noble gas configuration is written next. We're going to do a few of these so you can see them and make sense of them. They're a nice short way to do configurations. So, how to do shortcuts. Right? If you have a periodic table, you want to get one of those out. And I'm going to show you how to do the shortcut to this, okay? So, 1 through 7, this is our horizontal period or row numbers. And up here I have group 1 on the table and group 2, hydrogen and beryllium's group. We stick helium in there because helium ends in 1s2. So, at any moment you can look at the position of an element and say to yourself, I know the configuration in which it ends if I know this shortcut. And here's how you do it. You look at the row number, and that tells you the number of shells, the principal quantum numbers. And then you intersect that with the heading of what each group ends in. For example, group 1 elements all end in S1. They just differ by the number of shells that they have. So hydrogen ends in 1s1. Lithium ends in 2s1 because it's in the second row. Sodium ends in, big surprise, 3s1. 4s1 for potassium, 5s1 for rubidium, 6s1 for cesium, and 7s1 for francium. That's another reason, or the reason, why these elements are all in the same family, because they all end in S1 configurations. We carry that same idea to group 2, and it's not a big surprise, group 2, that they all end in S2 configurations. That's why we call groups 1 and 2 the S block elements. And it might be a good idea to shade those in a certain color on your table so you know that those are my S block elements. Right? Beryllium ends in 2, S2. Magnesium, 3s2, and so on and so forth. Okay, those are the S block elements. Another hint at this is notice that the S subshells can only hold 2 electrons because there's 2 S groups. The P block elements can hold a total of 6 electrons because remember there's 3 p orbitals and we start at group 13. Boron, look at boron's group. Boron's group ends in P1 all the way down to thallium, Tl. Right? So boron ends in 2, P1. Aluminum ends in 3p1. Gallium, 4p1. Indium, 5p1, and so on. These are called the P block elements, and big surprise again, that there's 6 groups because we cannot go past P6. The limit on p orbitals is 6 electrons, and there's 6 groups. Okay? Chlorine, for example, ends in row 3. It's got 3 shells, and it ends in P5. So it ends in 3p5 as in ending. Okay? And those are the P block elements. Groups 13, group 13, all the way to group 18. Okay, now notice here, there's no helium. Think back where helium ends. Helium ends at 1s2. So helium is actually placed in group 2 because of its configuration. It only has one shell. Well, you can probably imagine what's going to come next. We have the S block, the P block. How many groups do you think the D blocks have? 10. They can fit 10 electrons. And those are our transition metals, starting in group 3. This would be, I believe, scandium, number 21. Okay. Now notice what happens here. Something tricky happens here. There's two things going on. Even though we're on the 4th row of the table, remember that the D block, or the D subshells, start in the 3rd shell. So the 4th row, these elements all end in 3D1, 3D2, 3D3, and then something happens here and here. Notice there's no D4 and there's no D9. These electrons are redistributed for stability. When we get into the D block, some strange things happen. So this element here, let's see, scandium, titanium, vanadium, this would be chromium, right? So chromium ends in 3, right? And then there's an S1D5 that happens there. Okay. The 5th row ends in 4 Ds. The 6th row ends in 5 Ds. And the 7th row ends in 6 Ds. D3, S1D5, D6, and so on. Okay. Once again, there's 10 groups because there's 5 d orbitals and each one can hold 2 electrons, which 5 times 2 is 10. And finally, the F blocks, rows 6 and 7, these are called the inner transition metals. Okay? And notice we're in the 6th row, but the F subshell starts in the 4th shell. That's why this doesn't say 6F, because the F doesn't start in the 6th shell, it starts in the 4th shell. Okay. A little rule of thumb here is when you're in the D block, -1 from the row number to find the configuration ending. So if I'm in the 5th row and I'm in the D blocks, I take away 1 from the row number. 5 minus 1 is 4, so they would start in 4D in the 5th row. For the Fs, you take away 2. I'm in the 6th row, I minus 2, 4. That's the F block. And big surprise, they start. There's 14 groups here that I tried to squeeze in. Okay? Okay, so let's get some practice of this, right? Noble gas configurations. So my configuration here, 1s2, 2s1. Not so bad, not so long. So here's what I do. I look on my table, and this right here, 1s2, that's my element helium. So I put helium in brackets that represents 1s2. And I write what's left over, 2s1. Not a big deal, not a long configuration. But they start getting really long, right? 1s2, 2s2, 2p6, we've hit our next noble gas. So to write the noble gas configuration of this, 1s2, 2s2, 2p6, that's neon. So all of that underlined, I can simply abbreviate by saying neon and write what's left over. 3s2. And finally, 1s2, 2s2, 2p6, that's neon, 3s2, magnesium, 3p6. All of this is which element? What's the 18th element? If you find it, you're going to come to realize that it's argon. So all of this underlined in green can be abbreviated by argon, 4s1, 3d3. 18 electrons, 19 plus 3 is 22. Right? And that's how you do noble gas configurations.